So let's talk about this a little bit. Maxwell-Boltzmann. Let's assume we wrote a class test, okay? And I plotted a graph. And on the x-axis of the graph, I plotted percentage for the test. Yeah? And on the vertical axis, I plotted the number of people that got a certain percentage. So if 10 people got 10%, you know, they'd be there. This would be the number of people that got 50%. And the number of people that get 100% is this much. So it's what they call a normal distribution curve. And they use these curves all the time. That's how they adjust the marks every year. So I've got three graphs there. A green one, a red one, and a black one. Now, what do you think about the red test and the green test? Which one was easy? The green one was easy. How do we know that? Well, most of the people got really good marks. Yeah. The red test, obviously really hard. Most of the people did badly. And then you got the black one, which is kind of an average sort of a test where the majority of people did sort of okay-ish. Now at Bishop's, our curves are slanted towards the right because you guys work really hard and you've got excellent teachers, obviously, and you do very well. So we get much higher percentage of people getting good marks. Now, why am I talking about results for a test? Well, we use a similar kind of distribution when we are talking. So, Nick, I hope you're looking at the same stuff we look at. Okay. We use the same kind of distribution curve to look at the energy of particles. So here's an experiment that was done. Now, I don't quite know all the details of it, so don't quiz me too much on it. But imagine here's a little black box, okay, or a little container, a box. And inside it, it's got like radioactive material, or it's got a gas with, you know, a gas of some material. And the whole thing is contained in a vacuum. And initially that little hole there, that little door is closed, right? So the stuff that's inside, nothing can come out. And then over here, you've got a wheel, and on the surface of the wheel is some kind of detective material that if any of this stuff strikes the the material, it leaves a mark, right? Now what they do is they simultaneously open that little gap and start rotating the wheel, so that the stuff that's inside can escape, shoot straight across and hit the wheel. And when it hits the wheel, it makes a mark. Now, if you're rotating the wheel, you're going to get a distribution of dots on that wheel. The particles that go out really fast are going to hit early, and the particles that come out slower are going to hit later as the wheel is rotated a bit. Do you agree? Now, I've actually drawn this picture with the wheel rotating the wrong way, but never mind. You get the idea. That gives us a distribution. It gives us some idea of how many particles here have got high energy and how many particles have got low energy. Yeah? So we get an idea of the spread of energies within a sample of substance. And this experiment was done by Maxwell and Boltzmann and their students. And it's been repeated many times and it's been confirmed. So it's a way, because if you think about a collection of matter, think about the air in this room. Do you think all the air particles have got the same amount of energy? No. They're bouncing around. Some of them are going faster, some of them are going slower. They crash into other ones, then they slow down, then they speed up. So there's a spread of energies. Like if we did a test, are we all likely to get the same mark? No. Some of you are going to get high marks, some of you are going to get low marks. Right? So there's a spread of abilities or a spread of energies. If you plot those on a graph with energy on the bottom axis and the number of molecules with a certain amount of energy on the vertical axis, you get a distribution curve just like we would have got for the marks. Now that sample of stuff represented by this curve, do you think that's a high energy sample in general or a low energy sample? It's a low energy sample. Most of the molecules have got energy down here on the lower end of the energy scale. So what do you think would happen to that curve if you heated the sample up? It would move to the right. The peak would spread out and move to the right. So that's what we get. That graph is telling you a number of things. It's telling you, firstly, that not all particles have the same energy because there's a spread of energies. It's telling you that there's always some very high energy particles. I'll come to you in a second. So because there is, even though it's low amounts, there are some particles with very high energy. And you get this with any sample. Yeah, your question?
So that second mark on the graph, is that the temperature would be the average energy?
No. Temperature itself is not reflected on the graph. It's only energy and number of particles. Although the temperature is a measure of the average kinetic energy. But the temperature isn't shown on the graph. Correct.
That is the average kinetic energy.
No, so these is the specific energy of this number of particles. It's not the average kinetic energy. Yeah. Yes? You probably could. There probably is some way of adding up all those energies and dividing by the number of particles and we can average. So those 2 points you can get, and then you can also see that there's no maximum energy because there's no maximum speed. Something can always go faster. Say again? The peak is the number of particles that have got the peak refers to the energy that corresponds to the most number of particles. So the most number of particles with a particular energy. Yeah, the maximum energy is up here. So this is zero energy, and that's like tons of energy.
So the mass, like on the check marks,
they move the curve. So that what their assumption is that the people in this year should be on average the same intelligence as the people last year. People aren't getting cleverer. So you want the same percentage of people getting 80% or whatever. Although if your government wants to show that the results are improving, you just move a little further.
So since there's no maximum energy, why do we put a zero?
Why do we put a zero?
Why is it touching the order?
It's not touching. Yeah.
On the other side.
On the other side, that's minimum.
So like the lowest.
Yeah. So zero particles had zero energy. All the particles had some energy. All right. Now, I'm not going to work this out or prove it to you, but the area under the curve corresponds to the number of particles. All right. If you can work out the area of the curve, and when you've done integration at higher level maths, you might have done it already. You can integrate the curve to find out the area, and the area will give you the number of particles. So, like I said, now what happens if you start heating this up? There is a low temperature graph, and there's a high temperature graph. So, how does the high temperature graph differ from the low temperature graph? More particles have higher energy, but therefore there's a greater spread of energy, so there's a lower peak. Because there's less particles with any one particular energy. The actual peak is lower. Right?
Is there the same amount of particles?
Same amount of particles. So the area under, if this is one sample, if this is the same sample, then the area under those two curves has to be the same. So if the curve does move to the right, then the peak must be lower. Right? So you need to be able to identify which is a high and which is a low temperature graph. We can give you a graph like this in an exam and say which sample had the higher temperature. Remember we spoke about activation energy. Yeah? So let's say there's a reaction, and for that reaction to take place, you need a certain amount of energy, EA. And we'll just mark it somewhere on the graph. It doesn't matter where. Let's say that's the activation energy. The area underneath the graph to the right of the activation energy would be the number of particles with energy greater than the activation energy. So that's the number of particles that can react. You agree? Now, obviously, if you increase the temperature, look what happens to the area under the graph. It increases, which means there's more particles with energy greater than the activation energy. And that's why increasing the temperature increases the rate of reaction. Since you've got more particles with energy greater than the activation energy, there are more particles that can react, there are more particles that are going to collide, and a greater percentage of those collisions are going to be successful. So that's one of the things you can see from this graph. Higher temperature increases the spread of energies, more particles have enough energy to react, and therefore the reaction rate increases. So this is the kind of thing we expect you to be able to explain in an exam. And you've got to relate it down to the rate of successful collisions. Notice it's not the number of successful collisions. It's the number of successful collisions per second. All right. So that's what we can learn from the distribution of energy in any sample. Yeah, we're back to the yellow writing again. So what does a catalyst do? Now I will demonstrate a few catalysts to you when we do the demos. Has somebody sent me a message yet, by the way? Did somebody send me a message to remind me? Hello? Anybody out there? Thank you. Teams, fine. Please remember to book the rates demonstrations. So what's a catalyst? Catalyst is a substance which can alter the rate of reaction without being chemically changed at the end of it. Right? You need to learn that definition. It's another one that we're going to be asking you. And there's all sorts of catalysts. Now, how do catalysts work? Well, they obviously have to, if they're going to change the rate of reaction, they need to affect the rate of successful collisions, or the rate of effective collisions. There's just a few points about catalysts which are important. And obviously we can ask you those at any point. What I didn't discuss with you guys, I just launched into this whole thing about rate, but I think it's quite obvious, so maybe we don't need to discuss it. Why are we so worried about reaction rates? Why are they so important? Why would reaction rates be important? Really?
So like for safety.
Safety? So how could it affect safety?
Or if you're doing like form testing,
Okay. Efficiency? Obviously, if you're trying to make a product, and the more you can make in a short amount of time, the more money you can make in a short amount of time. So, and it's not just about money. What about things like if you want to make ammonia? Why would you want to make ammonia? Well, you can make a good fertilizer, and if you make a good fertilizer, then you can. What do you do? You make one. If you want to preserve the number of people in the world, you want to make enough food to feed everybody, you're going to need fertilizer. And ammonia is one of the key ingredients in fertilizer. So you want to make it, but you don't want to make it in 20 years' time. You need to feed people now. So the rate of reactions is massively important, right? Commercially and for all sorts of other reasons. This is just an example of one catalyst and how it works. So it's quite difficult to get gases to react. And one of the reasons that is because gases are very dispersed, they're very diverse, and the particles don't collide very often. So now you want to get these things to collide. So a good way to get them to collide is not to force them to collide, but to attract them to a common point. So you get a surface to which the gases will stick. And it's a platinum. Platinum works very well for this, for all sorts of reasons. So if you have a platinum surface, gases will often stick to the surface. They won't be absorbed into it, they'll be adsorbed onto the surface. Let's just stick to the surface. When they do that, the bonds between the gas particles break down. So here's an O2 molecule. It's joined together by a double bond. It's quite strong. It sticks to a platinum surface, and the bond between the oxygens actually breaks, because now it's bonding with platinum. That means if a hydrogen molecule comes along, the hydrogen molecule will also be now attracted to the platinum, and the hydrogen can now interact with the oxygen because the oxygen is no longer bonded to another oxygen. So it facilitates the reaction. Okay, just facilitates the reaction. It's kind of like, I've heard this illustration given before, and it's a bit of a daft illustration, but I suppose it works. You know, especially in Europe, you want to go on holiday, you want to meet some chicks or some people. You go to the beach, and you're all sitting on the beach, and they're sitting over there, and you're like, can I just walk over there and introduce myself? No, it's going to look weird. So what happens is they put a bar on the beach, and the girls go to the bar to get a drink, and you go to the bar to get a drink. And now you're standing right next to each other, and now you can chat. Facilitates reaction. There we go. All right. So energy changes during reactions. You guys have seen these curves before. What does the catalyst do? So you guys have seen this business with the activation energy, the amount of energy that you need for the particles to react. What does a catalyst do? It gives you another curve. This dotted red line represents the reaction with the presence of a catalyst. And you can see that the activation energy has been lowered. And it doesn't matter whether it's an endothermic reaction or an exothermic reaction, a catalyst can have exactly the same effect. You get a new reaction pathway. So look at this. If we ask you how does a catalyst speed up a reaction, this is what you must say. The catalyst lowers the activation energy by providing a different reaction pathway. Now I know that's very vague, but that's all you need to know. You don't need to know it in any more detail than that. So the activation energy with the catalyst is now the red curve, which is significantly lower than it was. So now more particles have got the same, has got the energy required to react, so more particles can react, and you get more particles per second. All right?
So that slows down the reaction.
So catalysts don't slow down, they speed it up. You can get a negative catalyst, which would increase the activation energy, and that would slow the reaction down. Yeah. Would we call it a catalyst? You probably call it an inhibitor.
So like anti-rust stuff.
I think anti-rust stuff works differently. Anti-rust stuff puts a barrier between the two things so they can't react, which I suppose is slowing it down. It's making it more difficult. So yeah, it's increasing the activation energy because now they've got to get through this layer in order to react. All right. So you fill that in. Can I move on? So how does that look on the energy distribution curve, on the Maxwell-Boltzmann curve? Well, remember I showed you the curve and I said, okay, let's assume that's EA for a particular reaction. Well, if you add a catalyst, what does it do? It lowers EA. So it moves it to the left. So if that was the number of particles that could react originally, if we now lower the activation energy with a catalyst, you've now got a bigger area of particles that can react. Now suddenly more particles with enough energy to react, so you can have more successful collisions per second, and so the rate of reaction will increase.
Wait, so I'm confused about that black box there.
So the black part, the area under the graph is the number of particles. Now the area under the graph here is the number of particles with energy greater than the activation energy. So the number of particles that can react. If you lower the activation energy by adding a catalyst, you've now got more particles. Okay. So please note in my explanation here, there are now more successful collisions per unit time. Or you have to say there's an increased rate of successful collisions. Guys, you're going to fight with me still. I'm telling you now. In your class test, or hopefully it's your class test and not your exam, you're going to write down, oh no, there's an increased number of collisions. Or there's increased successful collisions. There aren't. If you've got a certain sample of matter, the number of collisions will be the same. It's the number of collisions, or might be the same if you left it for longer. But the number of collisions per unit time will be increasing.
Just say increase, rate of collision has increased.
Yes, that's fine. As long as you say rate, it's fine. Rate of collisions will increase, and the rate of successful collisions will increase. If you don't mention rate, and you don't mention successful, you won't get the mark. That's why I've underlined those words. Okay, can we go? So, this is just like a little summary. We've discussed now a number of factors that can affect the reaction rate. We said concentration for liquids, pressure for gases, surface area for solids. Temperature affects all of them, and then catalysts, depending on what reaction it is, and then we also spoke about complexity. So you should be able to say what is going to increase the reaction rate. What do I have to do to concentration and pressure? Increase. Surface area? Increase. Temperature? Increase. And then obviously a catalyst increases the rate. And which molecules, or how does complexity affect the rate? Lower complexity or simpler molecules. All of these things will increase the rate of reaction. So that's just a little summary slide. Sorry? We are going to go through those, yeah. Okay. So that's all the, those are all the factors that affect reaction rates. Now we need to know, we need to look at one or two specific examples. The syllabus expects you to know a few specific examples. So we've got to just go look at one or two. So catalyst examples. Now, there's a section of the work called chemical industry where you have to look at a few specific industries, and the one they look at is the fertilizer industry. One of the reasons is because it's one of the most important industries in the world. You know, food and food security is a massive issue. So, Haber process. I spoke to you about making ammonia. Ammonia is crucially important as a fertilizer, and you can get it from all sorts of natural sources, but they needed to make it. So, the drive from this came in the Second World War, when Germany was desperately worried about how to feed their population. And I think Fritz Haber was a German chemist, and he's accredited with this process, trying to get hydrogen and nitrogen to react. Why would that be difficult? Both gases? What else? Not noble. Tell me about the bonding in nitrogen. Nitrogen gas. Triple bond. Nitrogen doesn't like to react. That's why you can breathe it in. 90% of what you're breathing in, or 80% of what you're breathing in, is nitrogen. Why doesn't it react with you? Strong triple bond. It's not easy to get nitrogen to react. A lightning strike causes nitrogen to react and makes NO2 in the atmosphere. But you need that kind of power. So to get nitrogen and hydrogen to react is not easy. So this was a significant discovery, and actually iron catalyzes the reaction quite well. So all we expect you to know is that in the Haber process, you need to know this reaction, and you need to know the name, you need to know this reaction is associated with it, and you need to know that iron is the catalyst. You don't need to know how the catalysts work. All the catalysts work differently. Some of them we may not even understand how they work, but they work. So that's fine. We chuck it in, it goes faster. We're happy. Another important one is the contact process. Now you will learn more details about these processes when we do chemical industry. And you'll remember that it'll come back to you. The contact process is the process to make sulfuric acid. I don't know if you realize how important sulfuric acid is. You can estimate a country's wealth by finding out how much sulfuric acid they use. If a country is using a lot of sulfuric acid, it's an extremely well-developed country, because it's massively important in industry for all sorts of things. So how do you make sulfuric acid? Well, you've got to get sulfur trioxide to react with water. There's a number of ways to do that. We go through the whole process when we do the chemical industry mechanism. But for now, all you need to know is that this is an important process in the production of sulfuric acid, which is the contact process. You need to know that reaction. This is the step that is difficult to do. And what do they use? They use vanadium pentoxide, V2O5. Why is it called vanadium pentoxide? Not because there's 5 oxygens. What's the oxidation state of the vanadium? 5. There's a V down there, just next to chrome. Okay? So if each oxygen there is -2, then the total oxidation state of the oxygens is -10. There's 2 vanadium, so each vanadium must be +5. Got it? So that's the vanadium process, the contact process. Oxidation of ammonia to give nitric acid, another important chemical. To make NO is an important step in the production of nitric acid. Why do you need nitric acid? Nitric acid is another component used to make the fertilizer. Why are fertilizers so important? Because we need food. Right? And if you combine nitric acid and ammonia, that's where you get your ammonium nitrate, which is a very, very good fertilizer and also, unfortunately, a convenient way of making bombs. So all the terrorist organizations, the IRA made that famous because you can get large quantities of fertilizer, and if you just stick it in a corner and leave it, it turns into a bomb.
All that they use in
Damascus.
the recent one that they just used.
No.
And like some like a desert sort of device or country.
It was Damascus.
Oh,
So that wasn't a bomb. That was just a pile of ammonium nitrate, which was left. And ammonium nitrate is very dangerous if you just leave it. It goes through a number of changes, and it ignites a massive pile of fertilizer. The ammonium nitrate explosions have been responsible for the biggest industrial disasters ever.
yeah.
Say again?
Yeah.
Was it Beirut? The minute I saw that video, I knew it was ammonium nitrate. Because there's another example of, there's the Texas disaster. It's called the Texas disaster, I think. It was a ship. It was a flipping ship full of ammonium nitrate that detonated. And it's quite a story. It's the biggest industrial disaster in American history. Actually, 2 ships detonated. One went off and then another one went off behind it. A massive ship. The anchor of the ship is now a monument in a town, I don't know how many kilometers away, where the anchor landed. So what was happening is the ammonium nitrate, I'll show you the stuff. We'll actually do a little thing where I'll put water on it, and it gets very cold. It gets cold enough to freeze water if you dissolve ammonium nitrate in water, right? It gets very cold. That's how they make those cold packs. The problem with ammonium nitrate is if it dries out, the opposite thing happens. If it dries out, it gets hot. So if you've got a big pile of ammonium nitrate, it gets wet, and now it starts to dry out, it gets hot. And a whole bunch of changes, the actual reaction is very complicated, a whole bunch of changes take place, but it can detonate. And this ship was full of ammonium nitrate in bags. It also has to have organic material around it, and they always put it in bags, obviously. And when it's a fertilizer, they mix it with other stuff, which is normally organic material, because you're going to spread it on your crops. And that all goes to make it more dangerous. And so this stuff it was heating up. It was giving off heat and was heating up. And they were trying to cool it down by spraying water on it. The water was just boiling, so steam was coming off it. The ship got so hot that the ship began to distort, and the water in the harbor around the ship was boiling. The seawater in the harbor around the ship was boiling. It was giving off clouds of smoke. Thousands of people came to look. So there were people standing around the harbor, all watching. There were aeroplanes from news agencies flying around, reporting on this thing.
Yeah.
And the thing detonated. Thousands of people were killed. The wings were blown off the aeroplanes. The wings were blown off. The anchor landed something, I don't know how many kilometers is away. Okay, and then the ship behind it, the same thing happened, and that detonated as well. Massive disaster. So they're one of the biggest non-nuclear disasters. So when I saw that picture of Beirut go up, I realized that bomb. There's no conventional weapon that is big enough to cause that much damage. It wasn't nuclear because there was no flash, and there was a mushroom cloud, but there was no flash. It wasn't nuclear, and if it was nuclear, it would have taken out the cameras.
So what's the flash?
Sorry? What's the flash? Just the amount of energy given off. It's way in excess of that thing. Anyway, that's ammonium. So that's the process to make nitric acid. Platinum turns out to be the catalyst there. Fermentation of sugars to produce alcohol. Some of you guys may be partial to the odd. I don't know if you've developed a taste for beer yet. Anybody? No? Any of you developed a taste for beer yet? Yeah? Not 18 yet, so you wouldn't go near it. You and me about, yeah. So I'm teetotal. I can't understand how people drink beer. To me, it tastes awful. I can't. Anyway, but people who do drink alcohol are familiar with this reaction because this reaction turns sugar into alcohol, and the catalyst you use there is yeast. Anyway, I've spoken too much. Time to go. Oh, you can have a break. Yes, cheers. 5 minutes, eh? Not 10 minutes or 7 minutes. 5.
So be back at 11 past.
Yes.
think they need to put it out. This is that. That's a look at it.
Right. See if anybody's joined us on Teams. No. Okay, cool. Thanks for getting back on time. So these are just a few ones that you need. This is the fermentation of alcohol making, sorry, fermentation of sugars making alcohol. The catalysts that they use are enzymes. In biology or life science, they call catalysts enzymes. Enzymes are the things that catalyze natural reactions. And you found those in yeast. And then hydrogenation of unsaturated oils to form fats in the manufacture of margarines. How many of you eat margarine? Still eat margarine? Okay. When I was your age, almost everybody didn't eat butter. We all ate margarine. And nowadays, people are moving back to butter. So I suspect this reaction is a lot less important now than it used to be. I mean, margarines are still sold. But anyway, the catalyst they use for this, you've got two gases. Again, you've got hydrogen reacting with ethene. So you polyunsaturating the fats. You'll understand more of that when we've done organic chemistry, but nickel. So you just need to be, if we ask you a question on these, you need to be able to quote those catalysts. That's all you need for them from that slide at this point. This one, I've put it in just because it's internationally important. It's not important in South Africa because we don't have catalytic converters, but we should. Catalytic converters are a big thing overseas. Why? Because they clean up the exhaust system. The exhaust systems produce carbon monoxide as well as carbon dioxide. And carbon monoxide is a lot more of a problem than carbon dioxide because carbon monoxide is toxic. Okay? So what they do in the exhaust system, it gets the carbon monoxide to react with oxygen to make carbon dioxide, which I know it's a greenhouse gas, but it's less of a problem than carbon monoxide. Nitrogen monoxide is also produced in the car's engines, and that's also much more of a problem that causes smog. So what the catalyst converter gets the nitrogen monoxide to react with carbon monoxide to make nitrogen, which is not a problem at all, and carbon dioxide. And so it just cleans up the air. I doubt very much where you would get a question on that in our exam, but it's incomplete. Your knowledge on the use of catalysts and the importance of catalysts is incomplete if you don't know about catalytic converters. All right.
What did you say?
Your knowledge on catalysts is incomplete if you don't know about that. So that's why I've included it. But you wouldn't need to study that for the exam. Right, let's try and have a look at some exam type questions. So, have a look at this one. Calcium carbonate chips react with HCl. Now that's a reaction we've seen many times. Solid, we discussed it in quite a lot of detail earlier on. If 2 grams of lumps of calcium carbonate react completely with an HCl solution of 2 molar, 20 centimeters cubed of the HCl will be required to react completely with the calcium carbonate. Now here, as usual, the devil is in the detail. Okay? And you have to pay attention to the details. I was talking to Mr. Russell this morning about just some of the stuff we do and how he marks his work. And he gives these people, his classes, I think it may only be grade 10, but he gives them a mark for paying attention to detail. And it's kind of like the neatness mark that I give you guys. It's so that you get the details correct. Now, I do a similar thing, so if you miss units and that kind of thing in science, we take marks off. It's paying attention to the details. And this is a question where the details are really important. The overall thing, okay, you add a catalyst that goes faster, or you heat it up, it goes faster. Yeah, that's fine. But now we want the details. So here are various combinations of these reactants. Yes, calcium carbonate, 2 grams combined, used. So if you look at A represents one reaction. All right? B represents another reaction. C represents a different reaction. And the only thing that's changed is the amounts of things or the state of the stuff. So in A, you had 2 grams of calcium carbonate which was in lumps. So the state refers to the calcium carbonate, and it was in lumps. And you mix that with 2 molar HCl using 20 centimeters cubed of it. And the reaction took place at 25 degrees. In B, still 2 grams, still lumps, but now you halve the concentration of the HCl. So what do you know straight away? Lower rate of successful collisions. So it's going to be slower. You agree? But you had more of the lower concentration. Does the volume, I'll come to you in a second, does the volume affect the rate? Doesn't. It means it'll take longer, perhaps, because there's more stuff to react. But it doesn't affect the rate of collision. It affects the number of collisions. So it doesn't affect the rate of collisions or the number of collisions per second. Question?
So is the capital M like all the
Yes. Capital M stands for mole per decimal cube. So you get the idea. We're changing different things and we're affecting the rate. So what's the question? The question is, which graph goes with which set of reaction conditions? Now I want you, so you've got to match up A, B, C, D, and E with one of these curves. So which reaction is going to be the fastest? Which is going to be the slowest? Now, what about the curve tells you the rate? Let's just get that right. What about the curve tells you the rate? The slope. The initial slope. Because all the graphs land up flat eventually. Yeah? So it's the initial curve. So you go and have a look at that and decide for yourself, try and match up the reactions A, B, C, D, or E with the curves. 1, 2, 3, 4. 1, 2, 3, 4.
On that PowerPoint is more.
Okay, well then just try and match up 4 of them. There should be 5. 1, 2, 3, 1, 2, 3, 4. Why is there any 4?
The left side, sir.
Say again?
It's not to the left side. It's 5 1. One just joined it.
No, I only see 4. There's the red one, the black one, the blue one, and the green one. That's 4. That's a bit strange. How on earth did I?
So maybe it's just maybe one of them could guess. This could be extra.
Oh, there is one missing. There is one missing. I'll draw it quickly. It goes there. Between, so there is one missing. It goes here. Let me draw it. Sorry. Right. Oh. Okay, so you need to draw this black one on. Draw that black one on. If you're working on the laptop, it's harder to draw, but you can draw it.
Which one?
The black one.
It's what?
Draw it on, please.
The PowerPoint is different.
Sorry? So did you have it on?
So it's 5, but there's one that's different. That's fine. So you just we change it to yours.
Yeah. So decide which is A, which is B, which is C, which is D, which is E. Now, I'm not going to pretend that this is easy. I actually think this is quite hard. So look at one or two things, maybe jump to the extremes. When you've got things like this in life, I often do that. I jump to extremes. An extreme helps you maybe sort out. Oh dear, look what I've done. I've lost my reading.
It's definitely that on there.
No, I was messing about with it. We had a thing this morning. A talk, and I was messing about with it. And I obviously took it off and put it back on. What the heck am I doing? Anybody got all 5 done yet? I think so, yeah. Want it? Yeah? Can I go? I'm going to break my neck here today. What the heck have I done? Jeez. Alright. That's what I get. Anybody agree with all 5? Well done. Well done. That's good. Okay. So E is easy because you got the most stuff. You got 60 centimeters cubed of it. So I've colored these things in the color of the graph. So you're obviously going to get the most gas produced. So that's E. C is also easy because you got the least things. You got 2 moles here, 20 moles, 20 centimeters cubed of that. It's 2 molar, but you've got only 1 gram of that. So that's going to be the least. So those two are quite easy to sort out. Now, why do I say D is the fastest? Well, remember, 10 degrees doubles the rate. Sorry? No. E is the fastest, yes. E is the fastest. And E has to be, the initial rate is faster, and E has to be that curve because of the amounts, right? Why is it so fast? Powder. Okay. That's not volume. That's the surface area of the solid. It doesn't affect the rate, but it affects how high it goes. Okay. Yeah, it affects how high it goes. But the powder affects the rate. And remember, when you are going from lumps to a powder, the surface area is increasing massively. Okay? Remember I said to you, if you cut the thing into 4 pieces, the surface area goes up by a factor of, it doubles. But if you turn it into powder, the surface area goes through the roof. It's an exponential increase in surface area. So D is really fast, much faster than the others because of the increase in temperature. All the others, if you work out the number of moles, you'll see they're producing the same number of moles. So then why is B the slowest? Well, B has got lumps and it's only got 1 molar HCl. You're getting the same amount of stuff because you double the volume, but that's a slowing down factor, and so is that. Whereas with A, you've got a higher rate than B because you've got a increased concentration of it. Yeah.
C.
Yeah.
If that 1 gram is 20 centimeters cubed, is it only, do they still do it in 2?
Well, remember, no. So you remember, for all of this to react, it says here 2 grams will react with 20. So now half of this HCl won't even react. because only 1 gram, you've only got 1 gram of this. You need 2 grams of this to react fully with 20 centimeters cubed of 2 mole. So that's why you can only get half as much gas produced. Yeah, that's why. And this amount here is significant, eh? This is supposed to be half of that, because you'll get half as many products formed. This one is 3 grams, that's why this is supposed to be 3 times. This one here is supposed to be 3 times higher than this one. 1, 2, 3. It's a little, I maybe do it a little bit too high.
These 14 centimeters cubed, but how come it produces the same amount as
It's 40 centimeters cubed of 1 molar. So the concentration has been halved, but the amount has been doubled. So you get the same number of particles.
If then 2 grams reacts with 2 and
20 centimeters cubed of 2 molar.
yeah, and 23 with 3 grams E with there would be not enough.
But there's 60 centimeters cubed of the 2 molar. There's 60 centimeters cubed of it. So 2 grams reacts with 20 centimeters cubed of 2 molar. Right? But now you've got 60 centimeters cubed of 2 molar. So you've got more HCl. It's the same concentration, but there is more of it. So it's enough to react with 3 grams. If this didn't say 60, then this curve would have landed up here possibly. No. So there's a lot going on there. Right, here's a slightly easier exam question. This came from November 2010. Relation between potential, energy, and the course of reaction. It's one of those curves that you use to. Activation energy for the forward reaction is. Go for it. Activation energy for the forward reaction. Hands up for A. B. C. D. Hold on. Okay, so it's 5 minus 3. One of the products formed in a chemical reaction is a gas. Which one of the following graphs of volume versus time best represents the formation of this gas until the reactants are used up? All agree? Easy. So, this is not a very good question, but it actually did come out of November 2010. So you just have to choose a word for each of those. Have a go. 4 marks, 4 minutes. No, more than 4 marks. 1, 2, 3, 4, 5, 6. So I've got my numbering all backwards there. I don't know what happened. Fairly straightforward. Do you agree? Yeah? Straightforward learning word.
So it's a stuff like maybe the exception.
Yeah. Well, you could say the whole, there's not a lot of calculations or anything you can do in this. The only calculation we can do is ask you to work out the rate. So this is a practical that we are actually going to do, all right? And again, this is one of those questions where you might look at it and think, oh, flip, yes, I don't know what's going on here. Look at all the information they give you. And sometimes guys get lost in information. Learners use hydrochloric acid and sodium thiosulfate, and now you're already thinking, geez, what the hell is sodium thiosulfate? I didn't learn about that. I don't know what's going on now. The panic starts to rise. Don't panic. The question's actually quite easy. Use this stuff to investigate the relationship between the reaction and temperature. Oh, well, I know what happens with rate reaction and temperature anyway. Right? Increased temperature, rate goes up. Reaction takes place represented by the following reaction. Okay, so I've never seen this before. Don't panic. It's sodium thiosulfate reacting with HCl, making sodium chloride. I know what that is. Making sulfur solid. What does sulfur look like? It's yellow. It's a yellow solid, yeah? So this reaction is going to go yellow. Makes water and makes sulfur dioxide gas. So gas is going to get given off. They add 5 centimeters cubed, okay, here comes all the details. 5 centimeters cubed dilute hydrochloric acid to 50 centimeters cubed of thiosulfate. And I place the cross drawn on the paper. The temperature mixture is 30 degrees. So what's all this about the cross on a piece of paper? Well, measure the time it takes for the cross to become invisible. Why should the cross become invisible? So you're going to make sulfur, which is a yellow solid, and you can't see through it. So as the reaction goes on, the solution is going to become cloudy yellow, and then you can't see the cross anymore. So we'll actually do this experiment. We'll do it in class. And as soon as you can't see the cross anymore, then you stop the stopwatch, and that gives you an idea how fast the reaction is going. Then you heat up the solution and do it again. So they do it at 40 degrees, 50 degrees, and 60 degrees. Write down a possible hypothesis. Oh, that's easy. So go for it. Try those questions quick. 2, 4, 6 marks, 6 minutes. Okay, so hypothesis, that's fairly straightforward. Rate increases with temp. The name or formula of the product that requires the need to work in a well-ventilated room, that's going to be the gas, sulfur dioxide. And it says you can write down the name or the formula. Guys, please be careful with that. If they say write down the name, and they don't say the formula, then you mustn't give the formula because you won't get the mark. And vice versa. If they say identify, then you can write either. But just look at that, small issues, details. Apart from the one other variable that must be kept constant during this thing, because you want to make sure it's a fair test, you've got to keep the concentration of the solutions constant. Sulfur is the stuff that's going to do it, and why is it possibly not going to be 100% consistent? You know, when you decide when the thing is invisible, that's not necessarily going to be consistent. All right? So, actually quite easy questions.
So what was 2, sir?
Sorry?
What was 2, sir?
Number 2, sulfur dioxide. So quite easy questions, but again, you don't want to throw away marks unnecessarily. This was the question as it was written. I need to make a change to it just for fun of it. What is represented by 1 over time on the vertical axis? What does 1 over time represent? Say again? Right. And what conclusion can be obtained from these results? So these are the results of that experiment. Rate increases with temperature. All right. Say again. No, is the smell of burning from outside? Yeah. Now, if I had asked you, I haven't asked you, but if I did ask you in this question to calculate the rate at 30 seconds, sorry, at a rate of reaction at a temperature of 30 degrees, what would you have to do? Frozen. Okay. If I asked you to calculate the rate at, say, 30 degrees, what would you have to do? Sorry, draw what? Horizontal line.
I'm going to gradient.
Gradient of what?
Of the temperature time.
But how are you going to draw the gradient at 30? Tangent.
Oh, tangent, yeah.
So you have to draw a tangent at 30 and work out the gradient of that tangent.
Isn't the y-axis already the gradient? Yeah, the y-axis already the...
No, it's not the gradient. So the y-axis is already the rate. No, you're right. So you just read off the graph. No, you're right, actually. You're right. You wouldn't have to calculate it. So the rate of this reaction, well, that isn't actually the rate. That is representing the rate. Because the rate is actually defined by amount of thing divided by time. This is just 1 over time. It's directly proportional to the rate. So, good point. You can't. Yeah. All right, so that's it. That's it. Okay, so we need to go through the notes, and we might as well start that now. There's not enough time for you to get started into the worksheet. So let's go and find the notes quickly and just start looking through them. I'm not sure, I haven't asked. Hang on a second, but I know according to the, remember I showed you the term planner? We're back on track. We're bang on track. So, rates notes 2021. You had a question, Chanji? No, because temperature is not in rate. You don't use temperature to calculate rate at all. So I was talking nonsense. You can't calculate temperature from that. So, okay, let's just go through the notes. Remember, we're just looking here for anything that we haven't discussed or anything that doesn't make sense. And here you would need to perhaps make 1 or 2 notes to add in anything or make a note of something that you need to remember. So this is just talking about why rates are important. That's what that chapter is about, that paragraph. Different ways to measure rates. So we discussed that. I showed you this business of measuring the gas coming off. Do you need? No. You just need to know what different methods we can use. We could give you a reaction and say to suggest ways that you could work out the rate of this reaction. And so you need to see if there's a mass loss or whatever. So, I told you can do a reaction on a balance. Here's another way. Why would you collect a gas like this?
Also because you can see the bubbles.
You can see the bubbles? It's normally when the gas is lighter than air. Right? So you collect it by the downward displacement of water. You might want to write that down. Because if they use the words downward displacement of water, you might think, what the heck are they talking about? Downward displacement of water. You often do it like that when you're collecting hydrogen. All right. Obviously, the gas that you're collecting mustn't react with water, and then you collect it by doing that. But you can just use this is a gas syringe. You can just use a gas syringe. That will tell you how fast the gas is coming out as well. So those are just 2 different methods. This is the turbidity. This word, turbidity. What does that mean? Well, a precipitate is being formed. What's a precipitate? Solid coming out of a solution. Solid from solution. So a solid is formed from within a solution. I'm going to make that smaller.
How big the solid is.
No, so it's just if you've got a solution with no solid, and now suddenly a solid is made, we call it precipitate. It precipitates out of the solution.
I'm still measuring the rate. Are you measuring how big the solid gets?
No, you're measuring how much solid is there. Because as the solid is formed, it makes the solution dark or cloudy so you can't see through it. So that's the one we're talking about. But it's just words. If you haven't seen this word before, you might not know what it's talking about. Turbidity or precipitate. A solid is made from the solution. So those words are important. Color intensity. This picture here is supposed to be on the previous page. I'll just make it smaller. Maybe we'll jump back up. Color intensity. Now, I'm a bit annoyed that this is in the notes, although I shouldn't be. I'll tell you why I'm annoyed. A number of years ago, I was marking the final matric paper, and the question was asked about the test for double bonds for saturation, and the way they test for that is using bromine, and the answer is that the bromine decolorizes. Okay, the bromine loses color. Now, a more sophisticated way of measuring that would be using this machine, which is called a colorimeter. So it's saying the same thing. The answer that was on the memo was the bromine decolorizes. Right? A student had written, use a colorimeter to test the change in color. They knew what they were talking about. They were suggesting a more sophisticated way of doing it. I wasn't allowed to mark it right. I had to mark it wrong. Because colorimeter was not on the memo. And I had a massive fight with the senior examiner and all that kind of thing, and they would not, I would not accept it. So that's the case where you have to just stick to the script. The reason they do that is because all the papers in the country are marked with the same memo. They've all already been marked. And so we have to stick to that memo. Even if somebody comes up with something that nobody's ever seen and it's right, they often will not accept it. So stick to what you've been taught. Don't get clever in the exam. That's not the place to start inventing new.
What should we say?
So you can suggest this as a possible method, but that's fine to suggest it as a method. But when we ask you, just stick to what's been in the notes. pH or conductivity. If an acid is in the reaction is reduced or reacted away, so it's no longer acidic, then the pH will change. So you could use a pH meter to represent how fast the reaction is going. All right, different equipments that are used, that's just the names of them. You can also use this, which is not mentioned, conductivity. Now that's not mentioned in those pictures. How can you use conductivity in a reaction?
So with ions,
To measure rate.
can't you use something like ions or ion solution?
Well, if a salt is formed, salts conduct electricity better. So if a salt is formed, the reaction should become more conductive.
So this reaction is
Yeah, you wouldn't be able to do it in those reactions because they're all salts. But in a reaction where salt is formed, or maybe a salt is destroyed, so I don't know if there's a reaction here. No, we'll have a look at some of the reactions now. But if a salt is formed, if the ions are being formed, then it's more conductive. So you could use electrical conductivity to test the rate. Okay, units. The units of what? The units of rate they're talking about. What are the units of rate? It depends how you're measuring it. But more commonly, we use moles per second. Right? But if you were using the volume of the gas, then it would be, so we've spoken about that. That's nothing new. This is nothing new. I told you that rate is equal to the change in concentration over time. And there's the definition of rate that you are supposed to learn. And there's a full stop missing there. All right, so we'll go up to there. We'll carry on.